So back in Oxford, it's a Thursday afternoon in almost summer. We're almost summer. I'm here with planetary scientist, professor of planetary science at the University of Oxford, Neil Bowles. Neil, you uh, in 2025, you were the instrument. You were the head of an instrument on the lunar Trailblazer mission,
Hmm.
which unfortunately saw an early demise. Tell us what that instrument was going to do, and you still down in the basement of this building, you have a spare copy of the not a copy, but another full
Hmm.
instrument, correct?
It's pretty much a copy. We build two at once normally so that we've got a backup. So anyway, yeah. So what the Lunar Thermal Mapper instrument was and is, it's like a thermal camera that we can send to a planet or an object like the moon, so we can get very accurate temperature maps of the surface. Now, as well as doing the surface temperature mapping, which we can get from flying essentially like a thermal camera, we can also pick out different bits of the infrared spectrum, which looks at how the surface responds due to the different rocks and minerals that make up that surface. And so it has lots of ability to understand what the composition of the lunar surface is as well. So the Lunar Thermal Mapper instrument gets really good temperature maps of the surface down at sort of 50-meter or so resolution, from depending on the height of the orbit. So from the Lunar Trailblazer orbit, would have about 50 meters. As well as that, it can also map the surface composition, and that information is really important because we want to understand both locally what the temperature is doing. If you want to land a spacecraft there, then you want to put things down. You want to know what the environment's going to be like, the temperature, but also how that relates to the composition that we see, and how that might relate to, say, transport of things like water across the lunar surface and other items.
And you think that most if the water that is on the moon probably is primordial, most of it.
Um, on the surface, most of it will have been delivered by things like comets or asteroids
But in the
impacting. So, oh, in
interior,
the interior, that'll be primordial. Yeah,
and it's not in a liquid form, which is kind of
probably not. It's
hard to
probably,
get our heads around, but it's in a chemical
yeah,
form.
it's probably chemically bound up with the minerals and materials there.
And why is looking for water on the moon scientifically important?
So it's scientifically important because it takes a long time. It's a vacuum, right? There's no atmosphere around the moon. So if anything hits the moon, most of the water will evaporate immediately. You think about it. It's easy to boil a kettle on the Earth,
Right.
and that's big, and that's at one atmosphere of pressure. Well, atmospheric pressure bearing down on us. The temperature on the moon can get above 120 degrees centigrade, so that's easily enough to boil water under our atmospheric pressure. In a vacuum, it just instantly evaporates. It's gone. So what it takes a long time for that water to accumulate and build up. If it gets trapped somewhere, it has to get trapped somewhere cold, and that has to be cold for a long period of time. So what that can do is, if we could extract ice from the, say, polar regions, it would tell us how it was brought there, where it was brought from, and it would preserve a record of that delivery process in the solar system, which would then tell us a great deal of information about how things like water are moved around inside the solar system and eventually end up heading towards Earth, because obviously the Earth and the Moon are basically the same place.
And you don't know, you wouldn't even venture a guess as to how much water is trapped as frozen water ice in the permanently shaded craters of the poles. And I'm not giving you a hard time about that, but nobody really knows.
Nobody really knows. We see signatures that the water ice, or certainly hydrated material, is present. We've certainly seen small amounts of potentially the water were liberated during the impact of the LCROSS experiment, which was sent to the polar regions. Impacted the polar crater back in 2009. But we don't really know how much water ice is present. We know that there's spectral signatures of it there, so we think we see it from remote data. But until we've actually gone and sort of drilled it and checked out a sample, we won't really know how much is actually stored there.
So, what does this portend for future lunar colonists or people who want to put it like a science Antarctic type base on the South Pole, Aitken Basin, and they want to get water from these polar regions? Are they being too optimistic, or the Artemis program, which a lot of it is commercial? You have these space startups that want to use water on the moon if it's there. What is your initial thought?
They're not being optimistic. It could well be there. Whether it's in an accessible form or an extractable form, that's a question that we have to actually go do more measurements, either from orbit or from the surface, and actually investigate. And that's what a lot of these experiments are going to do over the next few years with the Artemis program and the commercial lunar lander programs. The thing to remember, though, is that there are other good reasons to go to the south pole of the moon. And that is that there are regions where the temperature is actually much more stable over the course of a year than they are on the rest of the surface. At the equator of the moon, or near the equator of the moon, the temperature varies between day and night by 200 odd degrees centigrade. But at the poles of the moon, where the sun is hitting at a very oblique angle some of the tops of the craters, you can actually get regions where the temperature is relatively stable, maybe minus 50 degrees C or so, for a large portion of the year. And they're in permanent sunlight or near permanent sunlight. So you've got plenty of energy falling on you, which you can use with solar power, and you've got a relatively stable temperature environment, which means it's much more accessible for placing equipment or for operating there. And you can actually manufacture quite a lot of stuff on the moon. You can do what's called in situ resource utilization. You can take equipment to the moon to then extract minerals out of the surface. And if you take something like hydrogen to the moon, you can then use that to make water. And hydrogen is very compressible and obviously lightweight compared to taking water itself.
And when do you expect to use the copy of the LTM in your basement? Will you update this instrument with new technology? Are you going to use that one as is and just make another copy of it?
We'll use it as is because we'd already built the spare unit up.
Okay.
And so
so you won't have a spare unit if you send it.
Yeah, we won't have a spare one, but we're building something for a mission called Comet Interceptor, which is very similar. So we've got loads of bits we can reuse.
But when would you actually use the one in the basement? You mentioned something about a potential mission that's under study at NASA JPL in Pasadena.
Yep. So
tell me about that.
So we are involved in a mission called USIS Moon, which is the principal investigator is Abigail Freeman at JPL. And she essentially proposed to take the instrument that we lost on Lunar Trailblazer and put it on a rover. But then NASA said, if you've got the spare parts, then we should put it on an orbiter and try and repeat those measurements. So hopefully by 2028 or 2029, we should be in a position to refly the spectrometer that was lost on Lunar Trailblazer, and hopefully as part of that, we'll be able to fly our Lunar Thermal Mapper flight spare as well. And so we can really get that science back.
And the mission last year that went awry had nothing, the problem was nothing to do with your instrument. It just...
Yeah, it was just space is very hard.
Something happened 2 days after launch, I think.
Yeah,
right?
So space is hard, and if you have any problems, they can be very difficult to rectify because you can't go up and fix it.
Well, we look forward to hearing more on this future mission. Thank you so much for your time today, Neil. Fascinating stuff. Lunar science is always, should always be a priority until we can answer some of these questions. Thank you.
Good.